So what I would like to talk about is two bits of work that I've been doing with a large gap in years between those two bits of work. And normally I like to have a title that really explains what I want to talk about and is at the same time quite short. Clearly, I've failed this time in the second goal because it's become quite a long talk, but it does explain that what I want to talk about is really a crossover of some techniques for reverberation mapping to something that is very topical these days, namely to determine the reproduction number of epidemics, that is to say how quickly an epidemic disease can spread in the population. Right, so to start straight off, okay, no it won't, yeah, okay, so I go back in time a bit to a quite old paper by now of Blandford and McKee, where they first proposed that you could map out the density, the gas density of gas, interstellar gas in emission line regions around the nuclei of active galaxies. So you have usually a central black hole, which gets mass fed to it, so it varies in a continuum. The continuum emission of that varies, and then that continuum emission gets reprocessed by gas in the interstellar medium, so you can map out how much interstellar gas there actually is, and that can tell you something about how you expect that black hole to continue to be fed from gas in the interstellar medium. So that was really the birth of what we now know as reverberation mapping of AGN. And then, of course, there's quite a lot of happened. There are lots of techniques were developed to actually do that problem. And where I came in was about 12 years later, together with a colleague, where we realized that if you formulate it in a particular way, and I'll get back to that, there's actually a nice way to solve that, which is model independent. So you don't need to put in some sort of parameterized model of the gas density. You can just directly do a form of mapping. And for me, that was then fine. I worked on that for a bit. In the meantime, I've changed careers. I now work for a national statistical agency. But and in the course of that, I came to be involved also within the Netherlands in trying to measure, trying to trace which part of the population actually has been infected with COVID-19 and what the best ways are to try and do track and trace in ways other than just asking people. So I became interested in determining also this reproduction number, which is a measure for how many people get secondary infected from other people within the population. And the measure of that is a reproduction number. A reproduction number is one, means one single person infects another person. If it's bigger than one, you can get very large growth. If it's less than one, then an epidemic will slowly die out. So coincidentally, the paper that describes how to measure that reproduction number was, again, there's a 12-year gap between that and the paper that I wrote, but it turns out that what you need to do is very similar. So let's have a look at what you need to do. The common element in those two problems is that you need to solve an inverse problem. Now, inverse problem, with that I mean you have an integral equation where the left-hand side is something that you can actually measure, and one part of what is under the integral sign you can also measure, and the thing that you really want to know is the unknown bit. So in reverberation mapping, the unknown bit, I hope that everybody can see my pointer, the unknown bit is this psi function here that in essence is the reprocessing of the continuum emission into line emission in an AGN. And of course, there is some delay that depends primarily on the travel time between the light coming from that continuum source and reaching the region where that light is reprocessed into emission. So there's a delay time, and in fact, if you follow the line emission at a certain time, then the continuum must have varied sometime back, some delay time earlier. So a larger tau means going further back in time. Now, with epidemics, you have the same kind of equation. The J is the number of people infected, say on a daily basis. And if they are infected because they came into contact with somebody that was already infected, then you have also this integral equation, because there's different delay times. Some people might be infecting people straight away, or there could be a week between it, especially if there's no symptoms. You don't really know whether you're contagious and therefore are infecting people that you come into contact with. So the two equations are very similar. You have things that you can measure, both on the left-hand side and under the integral sign, and you have the thing that you really want to know. In this case, this A function is the infectiousness, or the transmission rate that you want to determine from your data. So in AGN, in the reverberation mapping, the unknown is called a transfer function, psi. You have emission line flux and continuum flux that are measured. And the extra hurdle in the case of AGN is, of course, that you can't really measure every single day. You have to, if the weather is bad, or if you don't have observing time, you lose parts of your light curve, both for emission and for continuum. And in some cases, some of these sources are some of the year behind the sun, so that gives you a large gap in your time series. So that's a kind of problem that you need to solve when you have to deal with AGN data. With the epidemics data, the unknown is this contagion function, A. What you measure is you can try to work with the infection rate of the people that are tested positive, but then that becomes very dependent on the testing strategy. And if the testing strategy varies itself a lot in time, if some weeks a lot more people are tested than others, or if only particular parts of the population are tested initially, for instance, hospital staff rather than everybody, then that influences your measurement. So a much more unbiased measure in terms of epidemic, following an epidemic, is the people that are actually admitted to hospital because they have sufficiently severe symptoms that they need to be hospitalized. Certainly in the Netherlands, where hospital care is pretty much universal, everybody that gets ill will can go to hospital. The only extra hurdle in this case is not so much that you can't measure every day, because if you have good registers and a good registration procedure, you can measure every day. But you have under the integral sign the same function J, this daily infection rate, or the daily hospitalization rate, as you have on the left-hand side. And that causes some problems as well. I'll get back to that too. But what you can see is clearly I have the same kind of equation. So if a technique works on the AGN, then it's certainly worth having a go at applying it to this type of data. Okay, now I also put in the integration limits here because normally you assume causality. That is to say that in the case of AGN, the line emission cannot respond to continuum emission that hasn't reached it yet. So that in this formalism means that by definition your psi of tau is 0 for tau less than 0. So you can set the lower limit for your integrations to 0 without any problems. It just means I assume that things are causal. The emission lines react causally to the continuum lines. And on the right, you do the same. You say that people can't get infected by people that they haven't met yet. They can only get infected by people that they have met in the past. And in practice, also, you don't have measurements for an infinite amount of time. You've started measuring sometime in the past, and you get up to the now. So that is a total time, capital T. And then, of course, you don't follow continuously. Usually you report, for instance, with epidemics, you report on a daily basis. So your sampling is regular and daily. With AGN, if you're lucky, you can sample every day or every night. If you're unlucky, then you miss data points. Cool. Now, as it happens, what I was involved in, before I became involved with AGN, was helioseismology, where we also solve inverse problems. And there you have an enormous problem because you have very large amounts of data that you have to deal with. Certainly at the time, I'm talking now the early 90s, it was a large amount of data. And that means that you needed really fast methods to do this inverse problem. And the only methods that existed at the time were very slow. So what I first did, and that was in the early 90s, was come up with a way to speed up those calculations. Now, to explain a little bit about what that formalism does, is that you take this integral equation again, and I use a bit of shorthand. So I now have a discrete set of measurements for this emission line flux, which I have an index I for. And for each of those emission line fluxes, I have a continuum, the full continuum time series that I've managed to measure up to that point in time. So that is just this C sub I is simply a shorthand for what is up here, the continuum line flux. So what this SOLA method does is it determines a set of linear coefficients, those are the small c's with an I, so that I can combine with the data. If I combine them with these continuum functions, they're functions of tau. So what I do is I simply try to find linear coefficients such that this combination, this function of all of these little bits, little snippets of continuum emission time series approach or approximate, for instance, a Gaussian. I take a Gaussian because I can presume that if I only measure with finite resolution in time, that I can't at every single point in time delay determine my psi, that there was limits to how much time resolution I can get out in terms of my function psi. So this delta acknowledges that I won't have an infinite resolution. And then you can do that for a few different values of this tau zero, these target delay times, to find an estimate of my psi at that target delay time. So if I do that, if I find the right coefficients that produce this, then those coefficients, when I combine them with the emission line fluxes, Li, in this way at the bottom, then I get an estimate for the value of this transfer function at that delay. And the nice thing about this is that these coefficients C sub I, the small c sub I, you can determine very quickly. You do have to do a large matrix inversion, but you have to do only one. And before, with the methods up to that point, you had to do very many matrix inversions. So that was a speed up of the problem at the time. So you have, in principle, n data items, capital N, and each of those measurements, of course, has an uncertainty as well. So you have to take that into account when you do the inversion. And in the particular case of this continuum flux, you do also have to do some interpolation because this function here, this Gaussian that you want to fit, is a continuous function. So you have to somehow deal with that. So those are little bits and snippets that you need to add to make everything work. I won't go into all of the technical details. Okay. Now, one very important problem that is true for any inverse problem, any problem where you have to determine something under an integral sign, is that such problems are very, very sensitive to data errors. They really blow up if you just go ahead. If you set this delta to be some very, really, really small value, then you still get a number out here, but the error margin becomes essentially infinite, even with finite data errors. So that is a peculiarity of inverse problems. Mathematicians tend to refer to this as such problems are ill-posed. So you need to really take care, and that taking care is essentially saying, again, whatever way you take to solve this problem, I have only finite resolution, and I need to regularize to take into account that I can't have infinite resolution in my results. So that is something that is really important to keep in mind whenever you attack this kind of problem. Okay, if you really have perfectly regularly sampled data, so every single day you have a number, then you can take a shortcut, an even faster method than what I proposed before, and that is that you can apply Fourier transforms. These integrals like this continuum line flux is convolved, or is a convolution of this transfer function psi and the continuum line flux. Now, convolutions in the Fourier domain, if you Fourier transform this entire thing, this entire equation, then you get that the Fourier transform of your emission line time series, is equal to the product of the Fourier transforms of your transfer function and the Fourier transform of your continuum line flux, which you've also got discretely sampled. So if you have everything in perfectly regularly sampled, then you can just use a discrete Fourier transform, which is really quick. So it's tempting to just say, okay, I can Fourier transform my emission light curve, I can Fourier transform my continuum light curve. So I simply divide the one by the other and do an inverse Fourier transform, and hey presto, I've got my my transfer function. Just peachy. Please don't try that at home. If you do that, you get the unregularized solution, which is all over the place, and it makes no sense at all. You get all sorts of rubbish. And one of the reasons is that this Fourier transform can have zeros all over the place or be very small. It doesn't work. However, there's a trick, the regularization trick in this case, is that you do something similar, but you multiply above and below by the complex conjugate of the Fourier transform of this continuum line flux. Now, up here, that's just a product of things. Down here in the numerator, you see that you get a Fourier transform times its complex conjugate. So this thing here is always real, and well, it can be zero, but otherwise it's positive. So if I then add a little bit of a small constant term, and that is what the regularization is all about. If you do that, you get a solution that is approximately the right, and approximately in the sense that you've gotten a smoothed version. It's if you know Wiener filtering, it's a kind of Wiener filtered version. So it's a smoothed function that comes out of this if you do the inverse Fourier transform. So don't do the upper thing, do the lower thing, because then you get a nice regularized solution. And you have a dial, this mu, that's just a parameter that you can make larger or smaller to try and tweak it so that you get something that is not completely flattened by the smoothing, but still has some actual structure that your data tells you that it has. That sometimes takes a bit of tweaking and trial and error to find out what the right value is. Right, now with the contagion function, we have to pass the next hurdle, And that next hurdle is that we have these hospitalizations. So the number of people that go into hospital with COVID-19, both under the integral sign and outside. So if I were to try and do my Fourier transform trick, I see, hang on, I have a Fourier transform both left and right. So if I divide the two, then I get just one. And the Fourier transform of an inverse Fourier transform of that one is a delta function. So I always get a delta function out. Well, that can't be right. And it isn't, of course. So what you need to do is take that integral equation and first do an integration by parts. And what that achieves, and I won't go into all the details, actually there's a paper on ResearchGate where I've written out all of the details of this. So I would refer you to that paper to actually look at all of the technical bits and bobs, which is a bit boring to go through in a talk like this. But what you do is, in fact, you get then this kind of thing. Again, it looks like a regularized solution, doesn't it? You have the Fourier transform times its complex conjugate here at the bottom, and I have some mu, a dial that I can twiddle with to get a good regularized solution. But this C, what is this C? You haven't seen this C yet. Well, that's the cumulative number of hospitalizations up to that time that you want to have that hospitalization for. So it encodes how the hospitalization rate has developed over the past weeks, months, whatever. So if you do it in this way, and taking properly into account that you have to then determine the Fourier transform, the inverse Fourier transform of a time derivative, then this is the kind of thing that you get. So in practice, yes, you can solve this, but you have to take one extra step to make sure that the problem satisfies the same kind of scheme that it did before. All right, so fine, it seemed to work, so let's go and try what that does. Now, I've talked about the reproduction number and this contagion function. The reproduction number is really the integral of this function A, the integral from 0 to some capital T, and that also means that the reproduction number then depends on this capital T. The longer time goes by, you get different reproduction numbers. It can be quite large when you have the start of the outbreak, and then if you get everything under control, it'll decrease over time and hopefully go back down to values below 0. Also, and I didn't mention that yet, in this expression that I had here at the bottom, also something with a capital K appeared. Now, that comes from the fact that in the case of epidemics, you have to take into account that some of the people that are coming to hospital might have been in another region and have moved back, for instance, after a holiday period where they got infected somewhere abroad, and then come to a hospital in the region where you can have your statistics. So in the case of the Netherlands, people that got infected somewhere else and came back to the Netherlands and then possibly also infected other people, but that is an exogenous contribution to the hospitalizations rather than endogenous, i.e. Having been infected by somebody else that is also already in the Netherlands. So you can determine this K by insisting that causality always be satisfied on this A. So those are little extra bits that you need to add in order to be able to solve the problem and find the complete analogy between active galactic nuclei and reverberation mapping and determining this reproduction number. Okay, now some of you might be familiar with the Netherlands. I wasn't going to assume that everybody would know what the Netherlands is like. In the top left-hand corner, I have plotted a little map of the Netherlands from Google Maps. The gray line that you see is the border, And the Netherlands is a fairly small country in northwestern Europe. It has a population of about 17.4 million, and that means that the population density is about 420 per square kilometer. So I was trying to look, are there areas in the US that I can sort of tell you that, well, the areas are kind of similar in terms of population density and the kind of what you could expect in terms of contagion and people getting in contact with each other and being infected. So I found two areas that kind of match in the US. One is the greater Los Angeles area, that's the bottom plot here, which has 18.7 million people, so almost the same, but it's a slightly bigger land area, so you have a slightly lower population density in this greater Los Angeles area. So that's not just Los Angeles itself, but also the area around it. I think it's called the Common Statistical Area or something along those lines. The National Census Bureau in the US has a formal definition for this area. So this is kind of similar. And then what I think is often known as the tri-state area is in the top right-hand corner. So New York and the region around that has more people, 22 million rather than 17, and is also roughly similar, perhaps slightly smaller in total area, so you get a somewhat higher population density. But this is the kind of thing that you have to think of. The Netherlands is kind of similar to the tri-state area or the greater Los Angeles area in terms of total population, population density, something along those lines. The only difference, you might say, the Netherlands, the age distribution in the Netherlands is slightly grayer, slightly more skewed towards slightly older people than overall is the case in the US. I mention those things because they're kind of relevant for epidemiology, population densities, things along those lines. Now, in the Netherlands, that's where I had data because there's a bureau that registers the hospitalizations due to COVID-19 and publishes this as open data. So I could lift the data from there and try and play around with it and analyze that data. Now, what I've plotted here is slightly unusual in the sense that I'm plotting the logarithm of the number of hospitalizations also against the logarithm of time in days. Normally, this axis is plotted linearly, and I guess it's bad because most epidemiologists think that an epidemic starts out as exponential so that you get a nice straight line in a log linear plot. But if you take a view that people don't meet at random anyone in a particular region, but only their contact network, then actually you'd rather expect a polynomial kind of dependence, so straight lines in a log-log plot. Now, certainly in the run-up into this peak, this is reasonably straight line. Of course, the first few days are slightly wonky, and then once the peak is passed, it starts decreasing. This is data up to the end of May. After that, there is more data, but I didn't analyze that for the paper that I wrote, which was over summer. The hospitalizations in the Netherlands have continued to decrease. The number of infections in recent weeks are increasing again, but that tends to be a rather younger population that doesn't get hospitalized. So the hospitalizations have not increased after this. So, okay, I go through my machinery and I then can get this epidemiological transfer function out, which I'm plotting here. So and on a horizontal axis, I have time. I've now plotted time linearly. So delay time, for negative delay times, it's nicely zero. I've made sure that that was true by constraining this k, this exogenous factor, to have the right value to make sure that that's satisfied. And then I get for April the 2nd, for all of the data only up to April the 2nd, I get a nice peak with a delay of say a week or two. So the maximum in this infection rate is a week or two, people are infectious for about a week or two, and after that, further back in time, the influence decreases. And on April 18, that was already past the peak in the Netherlands, you see that this peak has also shifted back in time, and also the vertical axis is rather lower. So you get that this transfer function is decreasing with time as well. The infections are decreasing because of lockdowns, social distancing, and lots of other measures. And then on May the 4th, it's lower still. And if you then take the integral, you're just calculating the area under the curve. In all of these cases, you see that indeed the reproduction number at this earliest point, which was already on the peak, I would say on the plateau, is below 1, and then it decreases afterwards. So all of that seems very nice. It's model independent, which is quite a change of pace for most epidemiology, because most publications that I've seen, at least on this, all used models and then try to calibrate, parameterize models. So that is nice. I'm independent of any modeling, any assumptions on how contagions occur and how long somebody stays contagious. The odd thing, though, for me was that the numbers that I was getting out were quite different. Not at first. Here they were okay, but here I get out quite small reproduction numbers where the models or the model-driven results from people at the National Institute for Public Health all seem to converge back to 1 at some point, which I thought was kind of odd when the number of hospitalizations were clearly decreasing. So what was happening there? That was what I was then starting to worry about. Because, of course, if it's a new method, you want to not immediately disagree with everybody else who is more of an expert in the field than I am, because I'm not an epidemiologist. Okay, so then we come back to this very big issue in inverse problems generally, and in this particular one, very much so. And that is the part of the problem with ill-posed mathematical problems is that solutions are also not unique. You're very sensitive to the measurement errors, but the results are also not unique. So to illustrate this, let's suppose that I have found some A that satisfies this relationship. So those are those previous plots that I showed you. And suppose that I can find a function B such that this integral B convolved with J is equal to 0. Then just adding left and right hand side, you can see that A plus B is then also a solution to my problem, and the integrals of those are not necessarily the same. So clearly, I can find solutions with different values of this reproduction number that satisfy the equations. To illustrate this a bit more, let's suppose I make a fit to these hospitalizations, which is the blue line. This is an eyeball fit. It's not a formal fit in any way. I just want to have something that sort of looks similar to demonstrate the point that I want to make. And if you then go through the math, something that convolved with this blue function is 0. Does that exist? Well, yes, it does exist. There's a whole family of solutions, in fact, and I'm showing them in the bottom right. These P's are Legendre polynomials of some argument that is shown there, and I can choose any value I please for this small coefficient B and sum over an infinite number of terms, and any of those will always satisfy that the integral, the convolution integral, is equal to 0. So I have enormous width, in other words, spread of possible values, and therefore a quite large range of R's that in principle could be produced out of this. And that is not just my method that has this problem, it is intrinsic to ill-posed problems. And that means that that is the fundamental reason why the error margins quoted on the reproduction numbers become so big. is not data errors or registration errors or mistakes along those lines. It doesn't come from the measurement error. It comes from the fundamental problem that this type of problem to solve is ill posed. So you have some constraints in making sure that the actual A has to be positive itself. So that limits a little bit what kind of values for this function B, capital B, are allowed, but you still have enormous freedom, and that gives you a very large freedom in reproduction numbers. And that is therefore also true of all of those model-based solutions for R. You have a very strong non-uniqueness in the solutions, and that is something that we really need to take into account. So the lessons learned for me from this work is that, yes, indeed, you can produce a reproduction number without assuming any model, but it's a kind of a minimal solution. Minimal in the sense that you are allowed to modify it in the way that I just showed in a number of ways, and that is you can't really, on the basis of just the hospitalization data, then decide what the correct reproduction number is, which reinforces that really track and trace is necessary. You can't just rely on the hospitalizations and do this nice technique to get a reproduction number. You really have to try and find how many people have been infected by the person that I now have in front of me who has COVID-19, and track and trace them to get a better or different way of getting at this reproduction number. The actual propagated data error is very modest. When I looked at that, the margin of error was barely larger than the thickness of those lines in those plots that I showed you before. So that's not so much of the issue here. And why is this so different than what we encountered with collecting nuclei and the reverberation mapping of AGNs? Well, there is some uniqueness there, but the nice thing about AGNs is that there's a lot more variations on all sorts of timescales of the continuum and emission line flux. Lots of variation in that C means that you can exclude many more terms of this function that you could add and still get the same result out. So having lots of variation over lots of timescales means that you reduce the non-unicity quite a lot. So that is the nice thing about AGN, and the kind of unfortunate thing about this cumulative hospitalization number, it doesn't have a lot of structure as a function of time. Okay, so that was then almost the end of my talk. There are other applications. In particular, I didn't talk a great deal about this solar method because for the epidemiology, just doing Fourier transforms works quite well because you have perfectly equally spaced data. In other applications where I've worked on was helioseismology and astroseismology. There are a number of papers on that if you're interested. I worked on the time delays of gravitational lenses, which is a kind of restricted version of this AGN problem. I even worked on image reconstruction or deconvolution, because also that is, in essence, an inverse problem. And finally, I recently attended the European Astronomical Society meeting where people were talking about the measurements of the gravitational multipoles of Jupiter from satellite data, satellites in orbit around Jupiter, and that they wanted to try and reconstruct the density, at least in the upper atmospheric layers of Jupiter, using those measured multipoles. And that again is solving an inverse problem. I've only heard about this just before the summer, so I certainly haven't worked on it, but I think that's an interesting application and the one tenuous link that I have with planetary science for this talk. So thank you for letting me present this work.